Today we're going to look at STraTA, self-training with task augmentation for better few-shot learning. If you have been paying attention in deep learning in NLP, you may find out recent 3 years, the model architecture is pretty much fixed. Most people using transformers, pre-trained model, Roberta, that kind of things. And what's actually changing, what's actually being innovated is the way how we augment the data, the way we coming up with new training objective, auxiliary task, which you can see two of the very important components I just mentioned in this paper. And why is so special about this paper? Because it's very effective. You can see the effect. It actually trying to run a few experiments on the few-shot learning systems. For example, for SST2, which is a sentiment analysis task, it only run on the very, very slow data regime. Basically, it's 8 examples each class. And you can see, compared to the BERT-based model, it has so much better performance. It achieved 90% accuracies. On the contrary, the BERT-based model, if they train only on 8 example, A labels per class, which is only like below 60. So it's huge improvement, and even almost close to the model they train on 97,000 examples. So you can see that's a very, very strong, strong indicator that these methods this paper propose is working. Also for another task, science tail, it's also the same thing. It not only achieve the state of the art on the low few-shot learning setups on these 2 data sets, it actually achieved the state of the art on 12 different data sets. So that's why I'm just so shocked by the results, and that's why I feel it's so interesting. By the way, if you would like to receive more deep learning content, deep learning videos like this, don't forget to subscribe. You can also connect with me on LinkedIn or Twitter. All right, so this paper was published by Google Research at the University of Manchester, Harris. So it's very, very interesting paper. It has very complex setups. It's not very easy to read, not very easy to follow. That's why I'm kind of summarizing it for you. Okay, so it has 2 main different components. One is task augmentation, another is self-training. So let's just look into that one by one. What's task augmentation? It's basically to use a model generate like auxiliary data for your model to do fine-tuning. It is not really a fine-tuning that you are doing for your target task. It's fine-tuning that they call intermediate fine-tuning, which is to do some task that's slightly related to your final target task, but not exactly the same. For sentiment analysis example, what your final task is to classify a sequence of text. Is this positive or negative or neutral, right? So your auxiliary task will be slightly different from that. Maybe most in this case, in this paper, the auxiliary task is natural language inference, which give you 2 different sentences, and your model need to classify if there's entailment or a contradiction or as neutral. Okay, so it's very complex. Firstly, they fine-tune a T5 model on the natural language inference data, and then use this T5 model, a fine-tuned T5 model, to generate auxiliary task, and train their model, which is your base model, on this auxiliary task, and that's also called intermediate fine-tuning. After you fine-tune this, you use this model as a teacher to generate pseudo-label data, and train your student model. Also use this initialized model, use this intermediate fine-tune model as a base model to start to train on this pseudo-label data and the label data. And then you got your new teacher model, use this new teacher model to generate this label data, pseudo-label data, and train your student model based on this original intermediate fine-tune models weights, then train this model on this data. Okay, so I guess you probably didn't follow because it's super complex. So that's why we need to look into that one by one. So intermediate fine-tuning. What is intermediate fine-tuning? It's basically they want to fine-tune the model on the natural language inference data set. What a natural language inference data sets look like, it's basically give you two sentences. The facts are accessible to you. You have access to the facts. And the model need to classify, is this entailment or contradiction or neutral? In this case, it's entailment. So the angle in the task augmentation data, task augmentations, is to generate a lot of these kind of data. And also, this sentence should be related to what your task is. If your model is going to do a sentiment classification, and these two sentences should be sentiments related, because they will be better for your model to adapt the final task. So how do you generate this kind of data? Okay, it's definitely not trivial. They firstly need to train a model they can generate those data, right? So what they are leveraging is they leverage the natural language inference data sets because they have a lot of data points. It's almost 400,000 data points. So they use T5 model, which is a generation model, to learn how to generate natural language inference data. Original data sets was give you sentence A, sentence B, and your label is their relationship, right? What they are doing is they can swap this how they fit the data. They only fit label, sentence, and the model need to generate the sentence B. What it actually means is, for example, I give you entailment and the facts are accessible to you. The model need to learn, if you need to generate, the model needs to generate something sentence because you already tell I want to generate something is entailed to this sentence. So model will generate, basically paraphrase this sentence to you have access to the facts. That's what the model is doing. If you swap, there's you fill a label, there's contradiction, the model will generate you don't have access to the facts. So by generating these kind of data sets, you can you got a lot of data sets, right? Then where you can perform intermediate fine-tuning on your related task. What's actually interesting is they kind of train these generation models on the natural language inference data sets. Then the model will learn how to generate this kind of data. If you fit the sentiment analysis unlabeled data to the model, then the model will generate some contradiction or some entailed data examples for you. And that's what you can do to use intermediate fine-tuning. Okay, so maybe you are still a little bit confused. So let's just look into this example further. This is unlabeled text from SST2. How you get unlabeled text? Easy. You just look into the SST2 dataset, label dataset, and then remove the label, and then you get unlabeled datasets. And then feed this data to your fine-tune natural language inference generation model, T5 models, T5 3 billion model in this case. Then the model will have this input in the case of a list of breeds actors. If you want an entailment example, the model will generate very similar, semantically similar sentence. If you want neutral, they will just generate something neutral. If you want a contradiction, model will generate a contradiction. Then now you have label, you have sentence 1, you have sentence 2. Then you can use this data, this called augmented data, and use data to intermediate fine-tune your base model. So the model will kind of learn how some hidden knowledge of sentiment classification. Then when you do a self-training, model will adapt much faster in terms of sentiment classification. Definitely you can generalize this method to many other different tasks, not limited to sentiment classification. Okay, another thing is we just look into one more example, both heartbreaking and heartwarming. And if you want an entailment, this story is moving and touching, right? If you want a contradiction, they will just generate, this the fable is artful and sophisticated, but it's also heartbreaking. So generate contradiction 1. Then your model, what your model is fine-tuning on, your model is fine-tuning on this. You have so don't get confused. You need to fine-tune the T5 model generation model we should learn how to generate sentiment-related natural language inference data like this one. Then you do your fine-tuning on your real target base model. You fine-tuning on the natural language inference task. The model can adapt the sentiment-related knowledge. Then finally, we go to the second stage, which is self-training. So you have data generation model, which is not being used in the self-training, just to generate accelerated data, and use this accelerated data to fine-tune your model. Let's say you want to use Spur model as your target model, then base model, then you fine-tune this Spur model on this accelerated task, which is natural language inference on the sentiment-related task. Then finally go to the self-training schedule. So what the self-training schedule is, we're not going to talk about that soon. We're just slightly working on the overgeneration and filtering, because if you just use your fine-tune, your T5 model to generate a lot of data, augmented data, they won't be good because they will contain some low-quality data. So how to filter that out is important. So how they do that, they generate 100 outputs per input, but not all 100 output are created equal, right? So they use another natural language inference classifier, pre-trained one, to filter. If the pre-trained model NLI classifier has the same opinions on the generated data, the generated data is a sentence label, sentence A, and the sentence B. So you fill sentence A to this classifier, and the classifier sentence A and sentence B to this classifier. Sentence classifier will tell if they're entail or neutral or contradiction. If they have the same agreement as generated data, then they use this data example will be selected. Then perform intermediate fine-tuning on that on both natural language inference datasets, which contains 390,000 data points, and the task augmentation datasets, which is sentiment analysis related natural language inference data in my example. Okay, another is even harder. It's self-training algorithms. It's slightly complex. Why I say it's complex is because of like schedule, the sequence they applying these things is slightly complex. So what they do is they initialize the first model, the base model, which is you fine-tune your intermediate fine-tune model. Then they use that as a teacher model. They train their model, their base models, on the originally labeled data set, SST2 in this case, training data, labeled data sets, original data sets. Then they train a teacher model, then use this teacher model and feed this teacher model a lot of augmented data. Where this augmented data come from, I didn't really get that from the paper, but I can guess it's from augmented data, task augmentation data. So they use those augmentation data, which treat it as unlabeled data, then feed to the teacher model. Teacher model will predict something, will predict neutral or positive and negative sentiments in this case. Then your student model, which is initialized on the same model, same base model, which is an intermediate fine-tune model. They fine-tune their model, so they train the student models on the label data sets and also a pseudo data set, pseudo label data set, which is pseudo label data sets predicted by the teacher model. Then you got a new student, you got a student model, right? Then they use this student model, which is T plus 1, FT plus 1, as a teacher model in the next generation. So use this teacher model to generate new pseudo label data sets and train a student data set on the original label data and the newly generated or re-annotated pseudo labels. Then you train a new students and use this new student as new teacher model. And one thing worth noting is every time you train your students, you use the original base model, intermediate fine-tune model, which is F0 as initial weights, and you train this student on the original data and the newly labeled pseudo data as the new data. So it's not like you always use the newly trained model as initialization for your student model. You always initialize to F0. So that's one thing that's different. And also what the tips is like, self-training on a broad distribution of pseudo label data is important, because a lot of self-training methods, they only focus on very small amount of data sets. The model is very confident. And they found out if you do that, you will have overconfident model and poorly calibrated model. Why? What do I mean by that? Is model either be very confident on certain examples and very unconfident answers. It's like when model make prediction, it always thinks if this is positive or negative. It's always like the confidence level always very high. The confidence score is not correlated to the accuracy. That's what poorly calibrated means. So what's ideal calibrated? That means when the model is very confident, the accuracy should be high. When the model is not confident, the accuracy of the predictions should be relatively low. Okay, so the solution is to train that on a broad distribution of pseudo-label data, which means you should have very, very different distribution of pseudo-label data. That's what this paper is about. It basically generate as diverse as unlabeled data as possible, so that you can use it as auxiliary data to train your student. Okay, here is their results, right? They basically run these 12 different NLP tasks. And if you don't know these tasks, just Google them and you will know. And they basically achieve state-of-the-art on all data sets. So that's why it's amazing. If they just achieve on 1 or 2 or 3, you can say maybe it's not statistically significant, but it's 12, and by now a small margin. So I would say it's really amazing. And these are some data sets. This is a task. TA means task augmentation. They only do task augmentation, and this is self-training. And the STraTA means self-training plus task augmentation, and definitely always it got the best performance. And if you just look at 8 training examples per class, it's amazing. If you do the sentiment analysis, you have 3 classes, and you only have 24 examples for your whole data set, and they can achieve almost double in a and natural language inference data sets. It's double the inference score to the BERT-based model, because you can imagine the BERT-based model will have very poor performance because it's only fine-tuned on 8 training examples per class. How can you have a good performance, right? And after you're doing this very complex data augmentation, self-training, you double the amount of inference score. That's so incredible. You basically, what you're actually doing, you transfer the knowledge from largely labeled data sets, which is natural language inference data sets, to your target task on certain level. So it's also like using pre-trained language model. When you use pre-trained language model, you basically transfer the knowledge from the data set this model was pre-trained on. Let's say Wikipedia, Google book corpus. You transfer the knowledge to your final task. So that's why when you use pre-trained model, without pre-trained model, your performance will be very different. Same thing to this one. So, but its improvement is so huge that I'm so shocked. Okay, so you also compare to the BERT large model, just do a naive training on a BERT large model and the STraTA training on a BERT large model. You can see the performance in low data regime. It's so different. Okay, so let's just look into another one. SST2. Let's just look into SST2. You can see the BERT-based models. If you just got 8 examples per class, it's not even 70%. Right, and if you do the STraTA, 90% effort score. So it's 20% difference. You don't need any new labels. You don't need any kind of new label data. So what you only need is natural language inference data, which is public available. It's free. You use that and you improve your task by 20%. Okay. Can you imagine? If you want to use label data to improve 20%, you roughly, in this case, you roughly need 200,000 examples, my estimation, or 500,000, which is very expensive. It could be 10,000 to 30,000 US dollars. So you save those dollars by using this data augmentation and self-training tricks. So the way I see it is, firstly, knowledge transformation from natural language inference task, and also a better way of training in the self-training regime. Okay, so for the bird large model, same thing, 17% improvement if you use STraTA. And if you only use data augmentation self-training, you also improve a lot, especially data augmentation. It's task augmentation. But not really. In different tasks, self-training in the bird large model, self-training are more effective. So it's very hard to say which one is better, which one is more significant. But one thing we are very certain for sure, it's if you combine both, you got best performance. So what are my thoughts? My thoughts are this setup is complex and the high compute costs. You can imagine if you do the data augmentation, self-training. Self-training is like you keep training until it converge, right? So it takes quite a long time, and you need to use a lot of compute resources. It's not easy. And also the way you set up these pipelines is complex. But again, it's incredible. So my prediction is, if in the future, it will become mainstream once there's an integration with the standard library. For example, Hugging Face. If this pipeline is integrated in the Hugging Face, I guess most of people will start using that. And I think that's just a matter of time. This is really, really promising methods. So that's it for today. And if you would like to receive more deep learning videos like these, don't forget to subscribe. Your subscription is really my best encouragement to make more videos like this. Also, you can connect with me on Twitter or LinkedIn. Other than that, I will see you next time.